In this work, we present the representation model for XR content and its rendering method. The presenter is Yongjae Lee from Korea Institute of Science and Technology. First, the motivation. Remote collaboration brings us an economical cost reduction, since people don't have to be physically gathered to work together. In recent, with the emergence of VR and AR technology, many collaboration methods employing VR and AR have been suggested. For example, phone calls, video conferencing, VR meetings, remote assistant AR, XR collaboration. To enable the VR-AR collaboration, it requires specific content data. In the case of VR meetings, to build the virtual world 3D models and coordination of them are required as content. In the case of remote assistant AR, drawing information indicating what the worker should follow is required, as well as spatial information where the drawing is augmented in the display is also required. XR collaboration is all the information previously mentioned. To make the VR and AR content, there are many authoring approaches exist. In recent, many commercial products are used such as Unreal, Unity, and Amazon's Marion. They provide intuitive authoring ways, however, it is difficult to make XR content using them. They serve VR content or AR content authoring ways in a separate manner. In addition, X3D, XFreedom, XML3D are suggested to represent 3D content in a declarative way. However, since they are originally defined for expressing three-dimensional data, it is not adequate to adopt them for making AR content. On the other hand, ARML and KARML are suggested for representing AR content. Likewise, aforementioned one, these are not adequate for making VR content. In this work, we provide a declarative representation to describe XR content and a render that draws the content in VR and AR. For that, we defined new HTML tags that represent virtual objects as well as physical objects. Moreover, we devised an algorithm that interprets XR code differently according to the user interaction environment. Our method gives several advantages. With our method, XR content will be human and machine readable and comprehensible, and the content can be used wherever a web browser exists. On top of that, the content author has no need to duplicate the content for VR, AR respectively, and no need to have deliberation about targeted user interaction environment. Finally, creating content that includes physical objects is possible. We created content with Amazon's Marion. That is one of the traditional content making methods. Then, we investigated what phenomena occur when AR content is played in VR and when VR content is played in AR. The first case is when AR content is played in VR. In the left video, the AR content draws the drone model on the display when the device recognizes the drone image on the table. In the lower right video, we test the same content in VR environment. We can see there is no background. Moreover, we can observe no drone model since the drone model is supposed to appear when the drone image is recognized. However, the device does not recognize any real object in VR. The second case is when VR content is played in AR. The left video shows the VR content that contains the drone model and background. In the lower right video, the device shows the drone model since it recognizes the drone image. However, it also shows the background. Thus, the camera view becomes blocked by the background. This disturbs the user to understand his or her circumstance. To solve those two problems, we defined a new HTML tag set. We call this WXR tag. WXR stands for Revised Extended Reality. This XXL tag has similar features to the traditional one like X3D or XMS3D. However, also has distinct features. One of them is AR target attribute. Only the group and geometry tag have this AR target attribute. The AR target attribute has an URL as its value, and the URL indicates feature information of a real object. AR engine can recognize the real object by using this information. We make the XXL tag set by using Web Components technology, so it is possible for any content author to create a new HTML tags by extending hours to obtain their own purpose. This assures high scalability to the authors. This is an example code of XR content that is created with the XXR tags. Within this example, we can see the XXR object tag has an AR target attribute. Its value is an URL for feature information of a book. With this, AR engine recognizes the real book. Next, we devise a render that has an algorithm rendering XR content in VR as well as in AR. If a user places the content in VR, the renderer makes all nodes in the scene tree to be visible. By doing that, we can circumvent the problem that when AR content is played in VR, the background and 3D models do not appear. And if the user plays the content in AR, the renderer firstly makes all nodes in the scene tree to be invisible, then makes visible only for the nodes which are recognized by AR engine. By doing that, we can evade the problem that the background has camera view when VR content is played in AR. With the XXL tag and the renderer coming together, we can make XR content independent of the user interaction environment. This image shows an XR content. The XXL tag in this example has the AR target attribute, which indicates feature information of 6324-5p string image. In AR environment, when the string image is recognized by AR engine, the renderer renders the group tag and all nodes the group tag is having. In VR environment, regardless of the string image recognition, all virtual objects are rendered. Moreover, back to the previous two problems, with this XR approach, we can circumvent those problems and get the result we wanted. In AR, the device does not render background anymore, but still augmenting the drone model on the screen, as well as both the drone model and the background are shown in VR for the same content and the same XR code. Furthermore, using this XR approach, we can expect a collaboration between AR users and VR users. Our method offers a great opportunity compared with the traditional one. With the traditional approaches, the content author should make VR part and AR part separately, and associate them to seem as one XR content. However, with our method, some steps to produce XR content are omitted or hid by the renderer. This makes the process of creating the XR content simpler and shortened. Now, we are going to show the examples created by the prototype of our proposed method. The prospective scenario is when the collaborators play XR content in the different interaction environments, that is, a symmetric collaboration situation. The first example is the XR content for disjointing and jointing 3D printer powder cake. In AR, the renderer shows only the virtual objects that are recognized, and does not show the background. In VR, we can see all objects are rendered including backgrounds. Note that the background is a 360 image. The second example is the opening and closing of the boiler pipe valve. Similarly, all virtual objects are shown in VR, and only the recognized objects are drawn in AR. In this work, we propose XXL tags and the rendering algorithm to solve two problems of traditional approaches. The double cell tags are designed to have the AR target attribute and to achieve high scalability by expanding the HTML. The renderer is designed to have an XR content interpretation algorithm for rendering the content according to the user interaction environment. Our further work will be to generate backgrounds for VR user from AR user in pseudo real time, and to streaming it from AR user to VR user. We will evaluate our proposed method in a more complicated situation rather than simple examples like the previously shown one. Thank you for paying attention to my presentation.